Hello everybody! Welcome to Remote Learning. This unit is called Sequences and Series, and in this video I will tell you what they are, and then in the next video why they're cool, and then after that we'll do some stuff with them. So what are they? Sequences, you see several examples here, are just lists of numbers, basically. You have a collection of values that have an ordering where there's a first and a second and a third, and so on. A series is a special word just meaning a sum, only usually it's a sum where there's a pattern or a rule for each of the individual terms. Sequences and series could be infinite, like they just keep going forever, or they could be finite. There's only a certain number of terms. Let's talk about notation. We need some way of referring to each individual element in the sequence or the series. We need a way of saying, like, what's the first element, or what's the 79th element. So usually what you'd do is you'd have a variable with a subscript. By convention, we'll always call the first number in the sequence the first term, and then the second term, and then the third term. You might think, like, what else could it be? But you know how sometimes we start with 0? Like, you might think that the initial value is like the 0th value. That is not what we're going to agree to do with sequences. We're always going to call that one the first one, and the second one. So if we want to refer to a sequence in general, you might choose a letter like A, and then write a subscript. And we would say A sub... Oops, see, I'm doing it already. I'm used to programming where we zero index everything. All right, so the first element is A subscript 1, and then the second element would be A subscript 2 and A subscript 3. And each of these, just like any other variable, would actually represent a value. So that way, if you wanted to write down something about the 79th term, you could write A sub 79 as a way of referring to that term. One common thing to want to do is to write an algebraic rule that will tell you what the nth term in the sequence is. So let's start in the middle here. So I've got a sequence where the first term is 1/2, and then 1/4, and then 1/8. You might notice that these are successive powers of 1/2, so I can get from here to there by multiplying by half, and then multiplying by half again. So the way you would notate the nth term is you would say A subscript n, the nth term, equals 1 over 2 to the n. And then you could just double check that this makes sense by plugging in a couple values of n and verifying it's giving you the right number in the sequence. So when n is 1, that should give me 1/2. And 2 to the 1 is 2, so it does. When n is 2, it should give me 1/4, and it does. The reason why is because sometimes you might accidentally be off by 1. So for example, let's pretend I just said, all right, so 2, 3, 4, 5, it looks like the denominator is going up by 1 every time, so I should just do this, right? But if you go back and double check, when n equals 1, because A subscript 1 should be the first term in the sequence, I don't actually get 1/2 with this equation. If I plug in 1 for n, it's actually going to give me 1 over 1, which is a slightly different sequence. So what I'd really need to do is add 1 here. And now if I want to know what is A subscript 1, the answer is 1 divided by 2, which really is the first term in my sequence. Let's do another one. So this one, which is just alternating +1, -1, +1, -1, I put this in here just to show you that the sequences don't have to fit equations that you're used to seeing. They can really be whatever you want. There's a trick to writing down this algebraically, which hopefully will make sense when you see it, but if you've never seen it before, might not come up with it on your own. So let's see, this is another case where we have to think, am I off by 1? So I know that if I have -1 and I raise it to a power, it's going to be -1 times itself a certain number of times, so I think that should give me the flip-flop. But is this actually going to work? Think about it for a second. Think about if you're going to plug in a value. Let's see. This is the first term in my sequence, so that would be A subscript 1. So -1 to the first power, ooh, that's -1. But that is +1, so that's kind of off. So I could do that, for example. And now when n is 1, I've got -1 squared, which gives me +1. And when n is 2, I've got -1 to the third, because it's 2 plus 1, and that's -1. So I think this is giving me the right alternation. Go ahead and see if you can put together on your own now what would be an equation for the nth term for that guy. Go go ahead, give it a try, pause the video. Alright, so for this one, really I just have to put together what I've got for this sequence and also for that sequence. So I'll start with -1 to the n plus 1, and that's just going to give me the plus or the minus, and so I'll multiply that by what I've got for this. Beautiful. Alright, so these are all explicit equations where you can plug in the term number that you want and the equation will tell you what is the value in the sequence at that term. This one might not be so obvious. Well, first of all, do you know this sequence? Maybe you don't. This is called the Fibonacci sequence, and the way that you get the next term is by adding the values of the previous two terms. So 3 plus 5 would be 8, 5 plus 8 would be 13, and so on. It's not at all clear what's an algebraic rule for the nth term for this one. There is one, and it's really cool, but that's maybe a topic for another day. What you can do, though, is you can write down that rule that I just said. I said the next term you can get by adding the previous two terms. That's a different kind of rule called a recursive rule. Recursive means something that's defined in terms of itself, which sounds kind of weird and circular, and I'll show you how to get out of that circularity in just a second. But let's start with just writing down what I said. I'd said that the nth term you can get by adding the previous two terms. So what's the term that comes right before a sub n? A sub n minus 1. And the term that comes right before that, I'm running out of space, is a sub n minus 2. Okay, you know, there we go. It's all on screen at the same time now. So this definitely describes how to calculate the nth term. If I want to find the 100th term, well, the 100th term is equal to a subscript 99 plus a subscript 98. The 99th term plus the 98th term. The problem is we don't know what those terms are either. And you could apply the rule again. You could say, oh, what is the 98th term, or what is the 99th term? The 99th term is the 98th term plus the 97th term. So you can apply this rule over and over again, but the problem is it needs to end somewhere. I can't keep saying, look at smaller items in your sequence. Eventually your sequence has to start somewhere. And so where your sequence starts, for us, is these first two. So if you're defining a recursive definition, you usually want to define a couple of small values where you just tell it the values. So here, a subscript 1 is 1, and a subscript 2 is also 1. So you think about those as the starting values, and then every value that is large... Wait, here, all right, I'm going over here. So every value, like n greater than 2. So if n is 1 or 2, we tell you the values. And then if n is larger than 2, we use this rule where you can compute the larger ones in terms of the smaller ones. So that's usually the idea for how you would define a rule recursively. All right, if you want a quick exercise, why don't you think about, for each of these, how would you define a recursive rule instead of an explicit rule? Go ahead, you could pause the video. Might be fun, might learn more. I'm gonna get a sandwich. All right, tricked you. No sandwich. I'm back. So here are some answers if you didn't think about them on your own or if you want to check. So I said in a recursive rule, you always want to start with a small example where you specify it directly. So a subscript 1 is 1, and then the nth term is just equal to the opposite of the previous term. That makes sense. So these two pieces together are going to define this alternating plus 1 minus 1. What about this one? So my first term is 1/2, and then my nth term is 1/2 times my previous term, right? Because if I have 1/2 times a half, I get a fourth. If I have a fourth times a half, I get an eighth. And in general, let's pretend I have, well, let's not pretend. I think that's probably good. Ooh, gotta keep all this stuff on the screen at once. All right, hold on. Woo. Probably, yeah, we'll edit that out later. Don't worry, folks. We'll take care of it all in post-production. So this one, this one's a little less obvious. let's leave these two. These are more good exercises. I just want to introduce you to some basic stuff right now. So you can think about this one. It's a good exercise. All right, let's talk about ways to notate a sequence. There's lots of them. So I've been writing the first couple of terms in the sequence just because I think that's a very clear way to see kind of there's a pattern and there's a sequence of numbers. It's more common to write the equation for the nth term of a sequence. You might also see this written with some curly braces. So this is an equation telling me what the nth term is. If you include curly braces, usually that's intended to, so like this, usually that's intended to imply this is shorthand for the entire sequence. So if I were to write it with the curly braces, we're not just talking about the nth case, we're really talking about 1/2 plus 1/4 plus 1/2 and then 1/4 and then 1/8 and then 1/16. So this is a notation that refers to the entire sequence. This is a picture of a college level text about numerical methods for approximating things. And if you look at this sentence, it says, these methods construct a sequence. Hey, that's what we're studying, sequence. And then this. So this is another way that you might notate a sequence. In that case, they weren't using curly brackets, they were using parentheses. They still have this idea of a subscript. What this means down here, you've seen me use this notation a couple of times. This means k is a member of the set of the natural numbers, this fancy n, which was hard to do in the fat Sharpie, by the way. This fancy n refers to the set of the natural numbers, which is 1, 2, 3, and so on. So all this is saying is, this is shorthand for the sequence x subscript 1, subscript 2, subscript 3, which is a generic way of specifying a sequence of numbers. So the point is there's lots and lots of different notations, and some of them are very easy to think about, and some of them look scary or awesome, depending on your perspective. But really they're all referring to the same thing. These are all ways of just saying, I am talking about a sequence of numbers. Okay, so you remember the word series just refers to a sum. Very often series are infinite like this. And a sum, in order to use the word series, the sum should have some kind of pattern in the terms. Might not be an obvious pattern. I want to introduce you to one more term. So there's a term called a partial sum. So if you have an infinite sum like this, if you have an infinite series, it might be interesting to look at partial sums. And I'll tell you why. Think about what is this series actually equal to? I mean, you know that some series, so like if I were to do 1 plus 2 plus 3 plus 4, clearly this is getting larger and larger. So if I ask what would this equal if I was going to add up all the values, you might say infinity. Infinity is not a number. Well, at least not a number that works like other numbers. It's like a special number. We have a special term for this, which is diverges. Diverges just means it keeps going up forever without actually approaching a number. But what about this guy? Does this also diverge? Or does it actually start approaching a specific value as you add more terms? A lot of people seem to know the answer to this already. A lot of people, when I ask in class, just immediately blurt out, that's equal to 1! And I don't know why you know this or how you know this. There's a nice kind of a very suggestive geometric way of thinking about this. Let's pretend this box is 1 by 1. So what's the area of the whole box? Oh, it's area 1. Okay, so what's 1/2? Here's 1/2. Do we agree? This is length 1/2 times 1 is area 1/2. What's 1/4? Oh, 1/4 is I take half of a half, like this. Okay, so this box is area 1/2, that's area 1/4. How do I add 1/8? Oh, it must be half of the fourth. And what about 1/16? Oh, it must be half of what's left over. So if I keep doing this process of taking what's left, dividing it in half, and filling it in, that's like adding each term in the series. And so if you ask, well, what am I getting closer and closer to here? As I fill in more and more area, I'm getting closer and closer to the area of the whole box, which is 1. So that's why you might think, huzzah, this is actually equal to 1. It's a very suggestive argument. That's not rigorous enough for most mathematicians. Really, I'm going to say all mathematicians. It's a suggestive idea, but we want to be a little bit more certain. Because I can give you arguments, I probably will give you arguments, where I'll give you a very suggestive looking picture like this for a sum, but it actually turns out differently than your intuition suggests. So cool, yes, but let's not trust it, let's verify. But how would you verify? So this is what I actually wanted to tell you to start with. The idea of a partial sum. So here's a partial sum. The word partial means part. And the word sum means sum. So I'm going to have a sum that is part of this infinite sum. And usually the way you'd notate it is with a subscript. So S subscript 1 is the partial sum. Well, let's pretend this whole series is called S. The partial sum that is subscript 1 would just be the first term. Okay, well, you might think that's not a sum yet. Okay, good point. The partial sum with two terms you denote by S subscript 2. So that would be 1/2 plus 1/4. With 3 as a subscript, that's 1/2 plus 1/4 plus 1/8. Probably could have guessed that. So, if it's really true that this entire sum is approaching a particular number, it should be true that these partial sums, as they get larger and larger as you're approaching infinity, should all be approaching a particular value. And that actually ends up to be the way that you demonstrate that infinite series converge. And you'll do a whole lot of that in calculus, and maybe a little bit of that in our class, depending on what we do. It's kind of cool and interesting, I think. It's like a nice little puzzle. Anyway, for the moment, the most important thing is this idea that if you have a sum and you want to talk about the sum of just the first couple of terms, you can do that with some subscripts, and that's called a partial sum. All right, that's the end. Let's just do a 1-minute summary. Sequences are lists of numbers. Series are sums, usually where the terms have a pattern. What happened next? You often want to be able to write down an equation for the nth term, and you can do that explicitly if you can figure it out, and all the terms always start with 1. Or sometimes you can write a recursive one, where you describe how to calculate the nth term using smaller terms from the series. But if you're going to do that, you've got to start from somewhere, and so you also have to include some term at the beginning where you just say what the number is. And then we said that there's lots of ways to notate a sequence, particularly writing an equation for the nth term, using curly brackets, or using a fancy notation like this for a general sequence. And last, we talked about series and how if you have an infinite series, you can refer to partial sums of that infinite series using subscripts. All right, so that's a lot of introduction. 18 minutes. That's fine. It's just like class. So what's next? Oh, I didn't tell you, why should you care about these things? Why is it interesting to study lists of numbers, or, lists of numbers, or sums of lists like this? Come back in the next video and I will tell you why.